In this video, we're going to take a look at radical expressions in their graphs, and a lot of this is material you've seen before. You've definitely seen the radical sign before and have had some experience with it. Now we're just going to formalize the process a little bit. First off, some terminology. We know that this symbol is the radical sign. But we also need to look at some other parts of this. Up until now, you are used to having some numbers in here. The number inside, underneath the radical sign is called the radicand. And the number on the outside is called the index. Now, usually the index is 2, and if there's no number listed there, we assume it's a 2. But we're going to look at cube roots and fourth roots and some other exotic roots in this chapter. And we need to know that the nth root of a means b to the nth power equals a. We are looking for some number that when we raise it to the index, we get a. And this can be exemplified by some numbers that you know already. For example, 8, you know that the cube root of 8 is 2, and that's because 2 cubed equals 8. So some stuff we've already seen before, just make sure that you are familiar with the terminology. So some facts about the nth root. If n is even and a is positive or 0, then what happens? Well, before I give you the rule, what I want to do is take a look at one of these. That means, for example, what if we had the square root of 25? Think about what that means. I think we already know that that means 5. And we know that that's true because 5 squared equals 25. So that's a good example for that. But isn't it also true that negative 5 squared equals 25? So really here, there could be two possible answers for this one. So we need some notation that helps us out here. So we say if n is even and we have a positive or 0 index, what we say is that the nth root of a is called the principal root. And in this case, we only look at the principal nth root of a. We look at the principal nth root of a, which means we're only going to look at the positive one. So when we say the square root of 25, we're going to refer to it as just 5, even though we know that there's another answer. And that opposite answer has a name as well. It is called the negative nth root of a. Most of the time, again, we'll only be looking at those positive principal roots of a, but just keep in mind that sometimes we'll want that negative nth root. The negative nth root will come into play when we start looking at equations where we want to consider more than one solution. But again, we'll just be looking at the principal root for the most part. Another fact about the nth root, if we have n is even and a is negative, what if we have a negative What if we have a negative inside the radical? Then what happens? Well, again, we want to use an example here. Think about something like this. What if we have the square root of negative 16? What happens then? Well, think about that. That means that we're looking for some number here. We're looking for some number so that when we square it, we get negative 16. And as of right now, we don't know any number like that. So in this case, we would say that the nth root of a is not a real number. So right now, there's no way for us to simplify when we have an even index and a negative under the radical sign. Later in this chapter, we'll actually have a way to do that, but right now we don't have a way of doing that. The third case is, what if we have n is odd? Then what occurs? So we're talking about things like, what if we have the cube root of 8? Is that something we can do? Well, that's something we can do. That comes out as 2. What if it's an odd number under there? Can we do the cube root of negative 8? Well, sure enough, we can do that as well. That's negative 2 because negative 2 cubed equals 8. So when we have an odd index, we're able to simplify these a lot easier, actually. And in this case, then there is only one real nth root. And there's only one of them. Unlike before, where we need to worry about a principal root and a negative root, here, there's only one answer. Cube root of 8 is 2. There's no other number you can cube to get 8. We don't have to worry about a negative here. There's only one number that is a cube root of negative 8. That's negative 2. So just some facts about evens and odds. I think if you start to just think about examples, then it comes across fairly easily. Let's see what else we have here. For any real number a, the square root of a squared equals the absolute value of a. Let's think about why that happens and why we need this rule. So let's start with some basic examples. If we say the square root of 8 squared, well, that's the same as the square root of 64, and we know that is the principal nth root, and that's 8. So it looks like that whenever we have a number squared under a square root symbol, we just get that number back. But the plot thickens a little bit when we start thinking about negative numbers. What if we took the square root of negative 7 squared? Think about what would happen in this example. Well, negative 7 squared, we know, is 49. Well, we know the principal root of 49 is 7. So even though we started with negative 7, this whole thing simplifies as positive 7. That's why we need the absolute value bars here. So whether we have a positive or a negative under that radical sign, as the radicand, we want to make sure we take the absolute value. A couple other examples here. It also means that the the square root of x squared, no matter what you put there, that comes out as the absolute value of x. And that's a small detail that you have to worry about. How about this one? What if we take the square root of x to the 4th? Well, what do you have to square to get x to the 4th? Well, this comes out as x squared, and I'd be tempted to put the absolute value bars here, but think about what happens here. X squared already makes this answer positive. So it's not wrong to put the absolute value bars here, but this just comes out as x squared. So sometimes we can simplify things a little bit further and think about them that way. Okay? So these are just some small rules about radicals. Some other small little rules here. In general, if n is an even positive integer, so if we have an even positive integer here and here, then anytime we're dealing with that, then we can take the nth root of a to the nth power. That will come out as the absolute value of a. So for example, here's a good example of that one. What if we took the 4th root of negative 2 to the 4th? Now, we don't deal with 4th powers and 4th roots all that much, but we can deal with it here because I gave you a nice small number here. Negative 2 to the 4th is 16. I want the 4th root of 16. This is one of the 4th roots that you should be able to do in your head. The 4th root of 16, that's 2, which is the same as what we had before, which is the absolute value of negative 2. So that's how that rule works. If n is an odd positive integer, then the nth root of a to the n power just comes out as a. So these are the ones we talked about earlier. If you have the cube root of 64, I know that this is the cube root of 4 cubed. It's one of the few perfect cubes I know by heart. And this will come out as 4. But it also works nicely. What if I did the cube root of negative 27? Well, I know that negative 27 is negative 3 cubed. And the cube root of negative 3 cubed will come out as negative 3. We do not need the absolute value bars here because negative 3 cubed does equal negative 27. So a little bit different rules for odds and evens. You'll experience some in class, and it won't be such a big deal. I do want to do 1 or 2 more examples. Let me see how much time we're up to here. 8 minutes. Okay. Let's see how much longer we can go here. Let's minimize that. Okay. So now we're going to look at some graphs. We'll look at the graphs rather quickly. So what does the square root graph look like? At this point, you know what a lot of graphs look like. Y equals mx plus b. You know what x squared looks like. You know what the absolute value graph looks like. This is probably a new one. And anytime we have a new graph, we do want to think about an xy table here and try to get some insight into what's happening. If I put in 0 for x, that's a natural thing to do. The square root of 0 is 0. How about if I use a 1? Square root of 1 is 1. Next one that's obvious to use is perhaps 4, because the square root of 4 is 2. Square root of 9 is 3. And you notice I'm avoiding negative numbers here. Like if I did negative 4, what happens here? Under the real numbers, I don't have any way to simplify that. So this is an interesting one, in that I have to worry about the domain here. The domain of this one is the set of all x's such that x is greater than or equal to 0. So we do have a domain restriction here. And if I plot the points, let's take a look at this. 0, 0 right here. 1, 1, kind of right here-ish. 4, 2, kind of right here. 9, 3, kind of right here. And if I were to go one more, if I went 16, I'd be up to 4. And 25, I'd be up to 5. So this is a curve that rises very slowly. And you notice I don't have any negative values for x here. Okay? So the square root graph is now one that's in your arsenal. Last graph to look at is f of x equals the square root of x minus 3. Again, to gain some insight, let's make an xy table. And the question really is, where does this graph begin? What is the lowest value of x I need? Keeping in mind that the stuff inside the radical, the radicand, cannot be negative. X minus 3 has to always be positive. And that only happens when x is greater than or equal to 3. So the domain for this one is a set of all x's such that x is greater than or equal to 3. So we can only use numbers greater than 3 here. If I plug a 3 in, 3 minus 3 is 0. Square root of that is 0. What if I plug in a 4? 4 minus 3 is 1. Square root of that is 1. And now I want to be a little strategic here, and you have to kind of read in between the lines. What would have to happen for me to get a y of 2? Well, that means somewhere inside of here, I would need to get a 4. That happens when x equals 7. Same deal if I want to get a 3. That means the stuff inside of here would need to equal 9. That will happen when we have a 12. And then suddenly I can have some insight into what's happening here. 3, 0 is right here. 4, 1 right here. 7, 2. 12, 3. Gets a little tougher. And again, there's our curve. It's basically the same curve. It's just instead of starting at 0, 0, it simply got shifted over 3. And we'll look at these graphs with a little bit more sophistication. So that's today's video on radicals and radical functions. And you have your notes there, and we'll look at some more in class.